So let's look at some graphical analysis of rates. So typically we'll do something very simple. A reactant will become a product. We're going to start with the first order rate law, which is rate equals the rate constant, a to the power of 1. So this is our first order rate law. Now we can take this rate law and do calculus, and we get what's called the integrated first order rate law, which is natural log of A equals minus KT plus natural log of A sub 0. The A is our concentration of A at time t. The lowercase k is our rate constant. The A sub 0 is our initial concentration of A. So I like to rearrange this equation so that I don't have to deal with the negative. And when I do that, when I take this equation, rearrange it, that's how I get this equation. It's the same equation. It doesn't matter which one you use, but you should probably be consistent because otherwise it will be confusing. Okay, so let's look at a problem. Given the decomposition of dinitrogen pentoxide follows first order kinetics, if the initial concentration of dinitrogen pentoxide is 0.25 molar and the rate constant is 5.1 times 10 to the minus 4 per second, what is the concentration of dinitrogen pentoxide at 3.2 minutes? So we're going to use our integrated rate law, which I've set up here. You want to make sure that you use the proper data from your problem. So in our problem, we were given the initial concentration, which is this one. So we'll put the initial concentration in there. We do not know the concentration at 3.2 minutes, so we'll put that in, that's our unknown. We put in our rate constant, and we put in our time. So please notice that the time was given in minutes, but I calculated it to be in seconds because my rate constant is in per seconds. So I'm going to go ahead and calculate this out. That simplifies to this. I have to find the anti-log button on my calculator. That's the e to the x button. I use that. And when I do the calculation, then I get 0.25 equals the concentration of N2O5 times this number. I solve for the N2O5, and that's my final answer. So this is basically a plug and check. Okay, so we could also be asked, how long would it take in minutes for the dinitrogen dioxide to decompose from an initial concentration of 0.25 molar to 0.15 molar? So again, what we're doing is we're going to use our integrated rate law equation. So I'm going to solve for the time. Looks like I left something off here. So this is going from 0.25 molar to 0.15 molar. Looks like I left off the 0.15 molar. 0.15 molar. That should be in the bottom here. I forgot to type that in. And then we're solving for time. So we get our time is this many seconds. And we have to be careful because it was asked for minutes. So we just need to change from seconds to minutes. So remember that we're using this setup, natural log of a sub 0. This was our a sub 0. Let me change my color here so you can see, because it looks like what I did is I just didn't type in the, I didn't type in the other one. Okay, so the a sub 0, that's this one. So here's our a sub 0. So that goes here. And then the a is on the bottom. That's this one. That goes here. And then you have one equation, one unknown. Okay, so there's another way that a question can be asked, and that is asking, here we go. Okay, that is asking for a length of time to convert a percentage. So in this particular problem, notice you're not given any molarities. You, of course, don't have the time because it's asking for the time. And we would have told you this is a first order rate experiment. So what you have to do is take this percentage and use it. So let's assume that the a sub 0 is 100%. Now we have a number. So the 100% minus 62%, that's how much you're converting, means you would have 68% at the starting material remaining. Now we can use our integrated rate law. Now we have some numbers. So the initial, we'll just call it 100. At time t, we've got 38. We have one equation, one unknown. We can solve for t. So in this question, it didn't ask you a particular time. So you could either leave it in seconds or you could leave it in minutes and you'd be fine. So you want to know how to do these kinds of problems with a percentage, because guaranteed you will get one of these problems on a quiz or an exam. Okay, let's look at the second order rate law. So the second order was rate equals k to the power of 2. So again, we take this and we do calculus and we get the integrated rate law. So the integrated rate law looks like this. 1 over a equals kt plus 1 over a 0. And again, the a is the concentration of a at time t. Our lowercase k is their weight constant. And this is our initial concentration of A. So this is our Y equals mx plus B. So we would graph 1 over A versus time to get second order. So if we look at the rate constant given, the rate constant is 7.0 times 10 to the 9 per molarity per second. And we're given the A, and we're asked the concentration after 2 minutes. And we're told it follows second order kinetics. So you want to make sure that whatever order it is, that's the integrated rate law that you're using. For second order kinetics, this is our integrated rate law. So now we're going to plug in the values. So 1 over A, which is what we're solving for. There's our K. There's our time. We're going to convert it because of our rate constant. And then 1 over our initial. And then we do the math. And we get 1.19 times 10 to the minus 12 polarity. Okay, so that's all we're going to do for the moment.